After the construction of the periodic table, it became very easy for chemists to predict the chemical and physical properties of elements. The properties seem to follow certain trends along a period or down a group. The periodic trends with respect to different properties will be the matter of our discussion. First, let us discuss about the atomic radii of elements. Before starting this discussion, we got to know a little bit about how atomic radius is conceptualized. It is impossible to measure the radius of an individual atom because there is no clear boundary of the electron cloud surrounding the nucleus. Now, what is the way out? The spacing between two atoms can be measured by X-ray crystallography. Half of this distance will give the atomic radius. Now, the atoms exist in nature in a bonded or non-bonded state. The bonds that are significant while measuring the atomic radii are number 1, covalent bond, number 2, metallic bond. Now, what is covalent bond? You remember that covalent bond is the result of sharing electrons of the two participating atoms. Therefore, there will be an appreciable overlap of the electron clouds of the individual atoms such that this shared part may be realized by both the nuclei. Covalent radius depend on factors like polarity of the bond and the bond order. In metallic bonds, the valence electrons detach themselves from the rest of the atom, forming a cation. These valence electrons form a sea of electrons in which the metal ions position themselves at specific lattice points. Half the distance between two metal ions in a metallic crystal is taken as the metallic radius. Van der Waals radius is half the distance between two atoms in a non-bonded state. One thing is obvious, that covalent radius and metallic radius is less than Van der Waals radius for a particular element. While studying periodic trends, we should not compare the covalent radius of one element with the metallic or Van der Waals radius of another element. Now let us study the periodic trends in atomic radius. For this purpose, I am taking the chart showing the covalent radii of elements. The elements of a period show a decreasing trend in atomic radius as we move across from left to right. This trend can be explained in the following manner. The atomic radius depends on two factors. Number 1, electrostatic attractive force of the nucleus on the outer shell electrons. Number 2, shielding effect of the non-bonding electrons. Now look at the second period elements. In a period, the outer shell remain constant. From boron onwards, the 2s electrons as well as the 1s electrons are expected to add to the shielding effect. But this does not happen in reality because more often than not, while forming bonds, the 2s electrons take part in hybridization and changes its orientation in space and thereby comes to the same level with the bonding electrons. So the shielding effect is due to 1s electrons only throughout this period. So what we see? We see that the shielding effect also remain constant. Only the number of proton increases by 1 unit as we move across a period. Therefore, the electrostatic attractive force on the outer shell increases and the atomic radius decreases as we move across. Now let us consider the atomic radius trends in a group, say the alkali metal group. As we move down the group, the valence electron is situated in the next higher energy level. The distance of the valence electron from the nucleus therefore increases so much that it cannot be compensated by the extra electrostatic attraction due to increase in number of protons in the nucleus. So, atomic radius increase as we move down the group. Now let us study the trends in atomic radii of the d block elements. Although it decreased somewhat initially due to increase in nuclear charge, but there is no particular pattern that is followed in these cases. This is because as the number of protons increase as we move across, the number of d electrons increase as well and screens the outer 4s electrons to cancel the effect of increased electrostatic pulling. Now watch period 5 and 6 over here. The atomic radius is more or less same here. This is due to these lanthanide elements which lie over here, and the phenomena is called Lanthanide Contraction, which you will learn in class 12. For the time being, just note that F block elements that lie in this position, the F electron shielding is very poor, which result in this contraction. Also look over here, just after the transition elements, these three groups in particular. The difference in atomic radius for these three groups is like this. For period 2 to 3, this difference is appreciable. There is not so much increase in the atomic radius as expected at this stage from third to fourth period. This is due to d block contraction, as d electrons cannot shield the outer electrons effectively from the increased nuclear charge. From fourth to fifth period, the difference again increases because in both these periods there is d block contraction. This one is due to 3d electrons and this one is due to 4d electrons. There is also d block contraction over here in the sixth period. These d block contractions result in inert pair effect of the 4s, 5s and 6s electrons, which is held more tightly to the nucleus. At this position, the contraction is even more because both d block contraction and lanthanide contraction come into play. So you see that the difference in atomic radius becomes very low over here. Thank you for watching this video.